Hi, Vlad here, DevInsideD.com. We're not done with the Scala playlist by a long shot, but we need some fundamentals to continue. So today we geek a little and see what's so special about binary numbers. Spoiler alert, nothing. Alright, so I got a magic glove here and a magic wand, but I have to warn you that I'm just a beginning wizard, so I'm not that good with it yet. Alright, so let's start. There are many ways to explain binary numbers, and I know at least two. There's one that I really like and the other one that I don't like. So let's start with the one that I don't like. Let's join the dark side. So in the one that you don't like, you just take a few decimal numbers that you know and you just write them all down. So let me start at the bottom. Let me go 0, 1, 2, 3, 4, 5, 6. I know it's really beautiful, right? 8, 9, 10, 11, and that should be enough for now, okay? And then you just go and in the binary system, we just use zeros and ones, right? So we just strike through everything that we don't like. Everything that does not contain only zeros and only ones, right? So 10, 11 is fine, and then we get 12, okay? So now what you do is you have a separate column and you write the binary numbers in there that are left, right? So you just have the 0, you just have the 1, then everything else is gone, and then you have 1, 0, and then you have an 11, right? So what we just produced is in decimal system, right? We have a 0, we have a 1, and then 1, 0 in binary is a 2 in decimal, and then 1, 1 in binary is 3 in decimal. But then you have a problem. In order to continue, you need to go all the way until 99, right? And then you're gonna have 100. So 100, if you have 100 over here, 100 in binary is gonna be a 4. So there are two reasons why I don't like this this way of explaining binary numbers. Is first, you still don't really know what binary numbers are, and second, it just takes way too long, right? What about the 1,000, right? Like in order to produce a 6, we need to go all the way until 1,000. So I'm just gonna remove all of that, and we're gonna do a little math today. All right, so mathematics can be dry sometimes, and in fact, the first few things that I'm going to say are going to be like really abstract, and they're going to be really, they might be really confusing. But then we're going to go through a bunch of examples, and everything's going to make sense, I swear. So let's start with a simple number like I don't know, 1337. Okay, let's just write it down over here. 1337. Now it turns out that this is just a very concise notation for a very general concept in mathematics called polynomials, right? We don't really need to understand what polynomials are. All we need to understand is that they sort of look like this, right? So it's a function where an x comes in, right? And then it just has this x and adds it to itself a bunch of times. Plus x, plus x, plus x. I hope that my pluses don't look like x's, all right? So the thing is that this is not the only thing that is happening, right? Because otherwise that would be just multiplication, right? This is the same as, x times 4, right? So what is also happening is that this x is raised every time to something different, right? So the first x is raised to some exponent, right? And the other one is also raised to some other exponent, right? So the x is always the same, the exponents are always different, right? Let me have an e3 here and e4, right? So different exponents. So first thing to note is that because we have this sort of raising thing going on, we also know that x is a base, right? So this thing is called a base, and this one is called an exponent. Sometimes it's also called a radix, but it doesn't actually matter to this discussion. Right, so what we're going to do now is let me remove all the x's. All right, so all x's are removed now, and we're just going to replace them with the word base. Right, in fact, I'm just going to use b, but you know that b stands for base, right? So we just have b's here, right? b, 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 b. All right, so and the next thing is happening that it also gets multiplied, right? So the b's, they get multiplied with some number, and this number is called a coefficient. It's a math thing, right? So we're just going to have some number, some other number, some other number, and some other number, right? The last one is actually not that pretty. Let me fix the last one real quick. Right, there we go. And let me also remove this circle. So for regular polynomials in math, there are some special rules, some special constraints. Like for example, this exponents, they're usually integers, right? So exponents, they're usually integers. This is just a notation, right? So it can go from, you know, minus infinity through 0 to the positive infinity, right? So from negative infinity to positive infinity. But in our case, we don't really care about that. All we care for us, right? So for us, it matters that these polynomials that they use to represent numbers, right? So the goal is to represent this number 1337 with a polynomial, right? So for us, we have basically only two rules. The first one is that the coefficients depends on the base, right? The coefficient, it can be only from, it can go only from 0, right? So the coefficient can only be smaller or equal to 0, or it has to be smaller or equal to base minus 1, right? So if the base was 10, for example, right, then our coefficients would go from 0 to 9, right? So 10 minus 1 would be 9. If our base was 8, why did I write the 9 there? Hold up. I obviously meant 10 minus 1 equals 9, right? And 8 minus 1 equals 7. And if we have a binary base, right, then we can only have numbers from 0 to 1, right? So there's always 0 here. Right, so from 0 to 9, from 0 to 7, from 0 to 1. And also another popular base is 16, right? So if the base was 16, let me draw it over here, 16 minus 1, then the last digit would be 15, but it's not really a digit. So what they did was, for the 16, they went from 0 to 9, and then for 10, 11, 12, 13, wow, I'm getting good with this thing. And 15, they just use letters, right? So 10 became an A, B, C, D, E, F. So in the hexadecimal system, you know, for 16, we have numbers from 0 to F, so to say. Okay, so let me remove all that real quick. The second rule that we have is that our exponents, they just go from right to left, and they just go from 0 to how many digits we have, right? So this thing over here is basically a digit, right? So this is going to be our number later, right? So you know, this is going to be, you know, in the end, this is going to be our 1, this is going to be our 3, this is going to be our 3, and this is going to be our 7, right? So our exponents, they are constrained just to go from right to left. Let me remove them. And they're just enumerated from 0, right? So this one is 0, this one is 1, this one is 2, and this one is 3. And this is an actual number, right? So it's not like E1, E2, it's the actual number 0, 1, 2, 3, and so on, right? So if we have 4 digits, then we go from 0 to 3. If we have 5 digits, then we go from 0 to 4, and so on. Now, in our example, we have a decimal system, right? So our B is a 10, right? So our base is 10, 10, 10, 10, and 10. All right, let me take the eraser, remove this, 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 and this, right? So our coefficients are now 1, 3, 3, 7, right? So it turns out that in real life, we're just used to the decimal system so well that we just got used to this notation, to calculate in this notation. But actually, every time you're calculating something, right? Every time you do 1 plus 2 even, right? You're actually calculating. You're doing your calculation with coefficients over a polynomial, and it's actually kind of cool, right? By the way, do you know why we use a decimal system? Well, here's a hint. You know, we have 10 fingers, right? And the word decimal comes from Latin. The word decim means 10, right? And this is where the decimal system is coming from. And also, it's kind of a funny thing. The word digiti, I mean, I think, I'm not sure if I pronounced it correctly, but it means fingers, right? So the decimal system, right, was 10 digits, right? It means 10 fingers. All right, so let's continue with this example. So what we're doing here is we're actually, well, because we're just explaining the decimal system, we're actually converting a decimal number into a decimal number. In all our other examples, we're going to take some system and convert it to decimal, right? So at the bottom, we will always convert to decimal, but in this first example, we're actually taking decimal and we're converting it to decimal, just to see how the calculation goes, right? Now, we're so used to the decimal system that calculating this whole expression becomes very, very easy, right? So we know that this is 1 times 1,000 plus 3 times 100 plus 3 times 10 plus 7 times everything to the power of 0 is 1, right? So it's 7 times 1, right? So the next step would be, okay, so this is 1,000, this is 300, this is 30, and this is a 7, right? And this is how we arrive at 1337. We just add them all together. This is the power of polynomials. Now, polynomials are used in math for many different things, but we don't really care about them today, right? So we're just going to go straight to the next example. Let's take exactly the same number, 1337, but in octal, right? And octal means base 8. Sometimes a notation like this is used, so we have a 0 and we have a letter O to denote that this number is octal, right? Because the octal system, right, base 8, it has less digits than the decimal system, right? So if you look at a number, all the digits, they could be from the decimal system as well, or they could be from the hexadecimal system as well. You don't really see it. So we need a special notation, and this is a notation. And the same goes for the decimal system, right? For the decimal system, sometimes you would do D. So this is going to be octal. The hexadecimal is going to have an X, and the binary is going to have a B, right? So this is always going to be the notation. I'm gonna leave this for a while over there, right? So let me remove everything that we don't need. So now that most of the things that we don't need are removed, let me remove the remaining ones. So now we're not converting from decimal system to the decimal system. We're converting from an octal system to a decimal system, right? And therefore our base is also no longer 10, it's 8. And because we're still using a 4-digit number, right? The exponents remain the same and everything else remain the same, okay? All right, so let's do the calculation. So in this case, we have 1 times 8 to the power of 3 is 512, and 3 times to the 8 to the power of 2 is 64, plus 3 times 8 plus 7. All right, so over here we have 512, and over here we have 192, and over here we have 24, 4, and over here we still have a 7, and now the result is 735, right? So I already knew the numbers because I did the calculation in preparation for this video, right? The first thing that you need to notice is that in the octal system, right, over here, we ended up needing more digits than we used in the decimal, right? Because the decimal system has more digits available, right? So it needs less digits to describe a bigger number, right? And in fact, this will play a role in the end of the video, where we're going to discuss why we actually use binary numbers for computers. All right, let me prepare the sheet for the hexadecimal example, and the number that we're going to use is F7CD. Right, F7CD. This is just a random number that I chose. I just chose it was 4 digits, so that we don't have to so we can reuse the 4 digits polynomial that we already have, right? So let me go and remove the 8s and replace them with 16s, right? And now our number is different. So our number is now F7C and D. And before we continue, let me actually have this tiny map over here. So 10, 11, 12, 13, 14, 15, there's no 16. Hold up, like this, right? So 10 is an A, 11 is a B, C, D, E, F. And you can also sometimes use small letters, it doesn't really matter, right? So let me rewrite this. So an F is a 15, right? So we have a 15 times this plus 7 remains the same, plus 12, 16 plus D is 13, right? So before we continue, notice that the binary system and the octal system and the decimal system, they can always be rewritten with powers of 2, right? Because 16 is a power of 2, and 8 is also a power of 2, and 2 obviously is a power of 2, right? So this can be rewritten, and I'm going to explain in a second why it's useful to rewrite it like this, right? So 16 is 2 to the power of 4, right? And again, we got 2 to the power of 4 plus 2 to the power of 4 plus 2 to the power of 4 and 0. This is a 4, obviously, right? So now let's repeat a little math so you can actually do this, right? So you can just multiply 4 with a 3. And over here, you can just multiply 4 with a 2. And over here, you can just multiply 4 with a 1. I forgot the times symbol. There we go, times, and this is a 7. And over here, we have 13 to the power. 4 times 0 is 0, Now we're going to talk about this in a second in this video, right? Why I did this, but basically, computer programmers or people who are like doing a lot of things with computers, they're really good with powers of 2, right? We just remember those numbers. So from the top of my head, I mean, obviously I prepared for my video, right? But from the top of my head, I know that 12 is 4096, and this is a 256. And this is a 16, which was obvious over here as well, right? And this, I mean, that one is kind of boring, right? Everything to the power of 0 is 1. Now, this still doesn't make this here easy to calculate, right? So you can still use a calculator. Now I already did that, so I'm just gonna write it down. So this one is 61440 plus 1792 plus 192, and we have a plus 13, and the end result is 63437, right? And by the way, the first time I was doing it, when I was writing from my calculator, I mixed up these. I mixed up these two. And by the way, every time you want to verify if your calculation is correct, just go to Google and say convert, this from, actually, let's do this real quick. So let's just say convert 63437, which is a number that we had, to hexadecimal, right? And it says it even over here, right? 0x F7CD, right? So I guess we did it right. Hold on, I didn't want to press this one. Let me do it again. Convert 63437 to hexadecimal, and I actually wanted to see this, right? So F7CD, so I guess we did it right. And you can do the same thing with octal and all the others. Notice again, and this time it's the other way around, that the hexadecimal system, right, it has more digits available. So it needs less digits to represent a number that would need more digits in a lower system. In this case, the decimal system is lower than the hexadecimal system. All right, let's finally get to binary. And for this specific example, I'm just going to remove everything, right, like this, okay? So for binary, we're going to take the number 73, which is apparently the best number according to Dr. Sheldon Lee Cooper from The Big Bang Theory. So he claims that number 73 in binary is a palindrome. It's 10010001, which backwards is 10010001, which is a palindrome. Right, don't confuse this with polynomial, right? Completely different word, right? So, but the calculation is the same, right? So we have an f, and in this case, our base is 2, right? So in our case, and I'm gonna have to write this smaller, right? It's 1 times 2 to the power of, I'm just gonna write the powers here, 0, 1, 2, 3, 4, 5, and 6. Come on, this is a 6, and this is a 5, right? There we go. Okay, so this is a 2 to the power of 6. Plus this 0, 0 times 2 to the power of 5, plus 0 times 2 to the power of 4, plus, now we have just 1, 1 to the power of 3, I'm sorry, not to the power of 3, times 2 to the power of 3, plus 0 to the power of 2, plus 0 to the power of 1, plus 1 to the power of 0. By the way, quick sidebar, the binary system uses the base 2, and every second number in every system just happens to be even, and even means it's divisible by 2. And over here, you always see that the last digit says if the number is even or not. So because it's not a 0, we know that it's not even, that it's odd, right? So we want to get to 73, right? So over here, we're going to have 73, and you know that 73 is odd just by looking at the last digit, right? But let's do the typical calculation, right? So 2 to the power of 6 is 64 plus, and notice that 0 multiplied was anything is always 0, right? And adding a 0 to something, it's basically useless, right? So everything that has a 0, we can just strike through. And this is not only for the binary system, this is for every system, right? So we're just going to have a plus 1 times 8 plus, and everything to the power of 0 is 1. Right, so what we have is 64 plus 8 plus 1, and it's the same as 64 plus 9. And every time I do this in my head, it's easier for me to add a 4 to a 9, then a 9 to a 4, right? So I always do this, right? So this is how we arrive at 73. So apparently 73 is the best number. So Sheldon makes a joke that 73 is the 21st prime number, and prime numbers are those that are only divisible by 1 and by itself, right? And he says its mirror, so 37, is the 12th prime number, prime, and its mirror, the 21, is the product of 7 and 3, which makes the number 73 somehow, right? And then he says in binary, 73 is a palindrome, which reads backwards and forwards the same, right? 1001, 1001, 1001. So there are many numeral systems out there. The most dominant ones are, you know, the binary and the decimal and the hexadecimal, and a little less dominant is the octal. But you can even create your own, right? Just pick a base and then you create your own system. For example, Alan Turing, the father of computing, he used to use the base 32. Like somehow it was easier for him. So we're almost at the end of this video, but before we answer the question why we use binary for computing, let us play with these numbers just a little bit, specifically with the binary system. And remember, I promised you to explain why computer programmers and, you know, everybody who's doing something with binary, something with computers, why they're so good with calculating the numbers. And that are just powers of 2, right? So let me remove everything over here. Let me write something down for you. So we're going to have a 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, and so on until I need 12, 6, 7. I need 12 because for the hexadecimal system, why did I start doing this? It's still a 10. 10 to the power of 9. For the hexadecimal example, we had to go to the power of 12, right? So 10 to the power of 12, right? So now we're just going to have a pyramid of describing how to write this in the regular notation, right? So this is a 1, this is a 10, this is a 100. It's going to look like a pyramid. This is 1,000, now I'm going to have 10,000, going to have 100,000, and now we're going to have a million, which is a thousand, which is going to be important a bit later. And then we're going to have 10 million. I hope I'm doing this right. Then we're going to have 100 million. I'm just going to do like that. So we're going to have the thirds, like, oh shit, I meant that. All right. So we're going to have 100 million. And then we're going to have a billion. Right. We're going to have the 9. So we're going to have the 0 over here. Right, and so on. You get the idea, right? So for the binary numbers, it's going to be the same, right? So if you have here 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, and so on, to 2 to the power of 12, and it keeps going, right? So if we were to write this thing in binary, right, it will look exactly the same as in decimal, right? So it's gonna, so for example, 2 to the power of 4 is gonna look like this. This is the 16, right? This is a 0, by the way. There we go, right? 2 to the power of 3 is an 8, and this is how an 8 looks like. 2 to the power of 2, this is a 4, and so on. So because we play with those numbers so often, then we just know, right? We just know, okay, this is a 1, this is a 2, this is a 4, 8, 16, and then I'm just going from memory, right? 32, 64, 128, 256, 1024, and I just know that this one is to the power of 10, right? So this one is 2 to the power of 10, and if I kept going, then this would be 2, 48, and this one is going to be 4096, and this is the one that we needed for the hexadecimal example. Also, by the way, notice that these numbers, they pretty much look like memory, right? Have you ever bought RAM? You know, 8 gigs of RAM, 16 gigs of RAM, 32 gigs of RAM, 64 gigs of RAM, and so on. The thing is that in the decimal system, right, we took 1,000, right, which is 10 to the power of 3. So we took the 3, right, which repeats every 3, right, 6 and 9, right? So 10 to the power of 3 is 1,000, and 10 to the power of 6 is 1,000 times 1,000, right? And over here it's a billion, so it's 1,000 times 1,000 times 1,000, right? So 3 times. Right, and we gave them special names, right? So for example, if we're talking about grams, you know, then 1,000 grams is a kilogram, right? Now technically, 1 million grams would be a megagram, but we just call it a ton. And then you would have 1 billion grams, and it would technically be called gigagram, right? But whenever I go there, right, we're just gonna say 1,000 tons, right, because of this 1,000 and this is a ton. So in binary, we took a number that sort of looks like 1,000, right, the closest number to 1,000, and we just took this, right? So so we know that 2 to the power of 20, and I'm just running out of space here, but 2 to the power of 20 is going to be 1,024 times 1,024, same as in decimal. So what we're going to do now is I'm going to remove everything, right? And we're just gonna do this thing with bits. So we're gonna have 1 bit over here, right? And 1 bit times 1,024 is going to be kilo bits, right? And 1,024 times 1,024 mega bits, and so on and so on, right? And then we have giga and whatever. And by the way, a byte, because we're never feeding bits to a processor, you know, when we're not speaking, like when I speak to you, we don't speak in characters, we speak in entire words. So with a processor, we took the same metaphor, right? So we're feeding the processor words, and somebody said, okay, the word should be 8, right? So 8 bits is 1 byte, right? So 1 bit, actually let's do 8 bits equals 1 byte, right? Also, there is a thing called a nibble, very not very well known, right? And it's just 4 bits, right? So now we're just gonna have a real quick table that is gonna do this. Okay, so 1 nibble equals 4 bits. 1 byte equals 8 bits or 2 nibbles. And by the way, forget the nibbles, nobody cares about nibbles. 4 nibbles. So 1 kilobyte, and I'm just making the B capital. I don't know why, it just happens automatically. So 1 kilobyte is 1,024 bytes, right? 1 megabyte is 1,024 kilobytes. 1 gigabyte is 1,024 megabytes, and 1 terabyte is 1,024 gigabytes. It should be, but this is not what you get when you buy hard drives, right? And I'm going to show you this in a second, right? So I'm not going to continue with this, but there's also peta. It's the same pattern. So we get peta, exa, we got zeta, and we got iota, and right now they're also discussed hella or Bronto, I think it's called. Right. So it's been estimated that Google has somewhere over here, somewhere between 10 and 15 exabytes, right? Which is 1,024 petabytes, which is 1,024 times 1,024 terabytes, right? I think I said it right. Now, I just did this whole calculation just to go to Amazon, right, and to find a hard drive that I have in my system, which is a Samsung. And by the way, this isn't what I'm going to tell you is not Samsung's fault, right? The whole industry is doing this, right? So I'm just going to click on this picture, on that one, right? And I'm going to show you that 1 gigabyte, it should be 1,024 megabytes, which should be 1,024 times 1,024 kilobytes, which should be 1,024 times 1,024 times 1,024 bytes. Now, I'm not going to do this calculation, but basically whatever comes out is not going to have a bunch of zeros. So what they did is they said 1 gigabyte is 1. So basically they made it look like a decimal, and they wrote it on their hard drive so that people can't sue them, right? That they're not actually giving them real gigabytes. And also plus, the actual usable capacity may be less because, the hard drive also needs a little bit of memory just to work. So this is why when we're going to look at my system, so this one, for example, this SSD, exactly this one, I can actually use only 931 gigabytes, right? So if you actually did this whole calculation, and I think I did it once for fun, assuming that the hard drive wouldn't actually need anything, right? So assuming that they would actually give it to us in such a way that they would just subtract whatever the hard drive needs, and they would actually calculate this in binary, we would actually have, right? So they would actually sell terabyte hard drives, which would have around, I think it was like 180 gigabytes more, right? So 180 gigabytes more space, right? The whole industry decided that it's better to sell less memory and to just, so that everybody just get used to this calculation. I don't know, maybe they thought that people are not smart enough to understand binary or something, or maybe it was just better for them, right? They just used it to sell less memory. And again, this has nothing to do with Samsung, right? Literally every hard drive, every memory stick, everything that you have is calculated like this. They all do this. All right, so I guess we're in the end of the longest video in the history of humanity about binary numbers. I guess nobody's gonna watch it because it's gonna be an hour long, but in any case, so we're just going to end it with a discussion about why do we use the binary system. So computers, they actually need to do only two things. Well, a processor needs to do only two things. It needs to do logic operations and arithmetic operations. Now, for logic, it's very simple, right? So 1 maps to true and 0 maps to false very wonderfully, right? For arithmetic, it's actually not so simple. In fact, we chose binary, right? But binary is the number with the least sort of the least possible combinations, right? So the least not combination. It has only 2 digits, right? So in order to represent a big number, it would need like way more digits than, let's say, a decimal system, right? So why did we choose it, right? Especially because in the day memory was not so cheap, right? So this was an actual concern. So what happens is that at some point, right, we have an analog wave in a wire, right, the electrical current, right, and we need to translate it into a digital system, right? So if this was a so this was a small graph, right, and this is time, and this is going to be the strength of the signal. And I'm not a physicist, but I believe it's measured in volts, right? So if we had a wave like this, something like this, right? And if we wanted to measure it, right? If you wanted to measure the volts, right, with a decimal system, right? So we would say that this was a 1, this was a 2, a 3, a 4, a 5, and 6, and 7, or something like this, right? Then we would need to be very careful, right? So let's do this, that, and that, right? So for example, look over here. So this should be 0, 1, 2, and 3, right? So this should be a 3, right? But if we so we always measure at some point in time, right? So this is like 1 second, 2 seconds, 3 seconds, right? Let's just say that the 4th second was here, right? So in the 4th second, we will want to measure this bit over here, right? This not this bit, but this information, right? So it should be a 3, right? But something happened, there was a construction or something, or I don't know, for some reason the signal was weaker, right? And then it just flicked into here, and now all of a sudden it looks over here like a 2, right? So all of a sudden a 3 became a 2, and this whole thing is avoided with just 2 states, right? So let me do this, right? So if we have the same thing, now we have this very, very flaky wave, right? By the way, wave can't do that, right? Let's do this, right? But then you just pick a threshold like this, right? And you just say, okay, everything is above is a 1, everything that is below is a 0. So no construction site, no weird thing is gonna make this look like this, right? Or this look like that, because the difference is just so great. And this is why we use binary, just 2 states. All right, so we're at the end of this video, and now you understand binary, or that's what you think, because we actually didn't talk about negative numbers, or what about floating point numbers, right? So how do you store a 1, 2, comma 3, 4, right? Or it depends where you are, 34.34. How do you store that? And this is exactly what we're gonna talk about in the next video, where we're gonna get back to our Scala playlist and see how these numbers are represented in memory, or to be specific, how they are represented in the Java virtual machine. All right, so I hope you liked this video. And again, I'm always gonna apologize for those videos because they're so freaking long. How could I spend an entire hour to explain something as simple as a binary system? In any case, I hope you liked it, and see you next time. Cheers.